I'm going to go over the new DOE capability in RecurDyn V9R5. And so some of the upfront advantages of this new DOE capability is that there have been some nice improvements to the user interface just to increase the usability of the DOE capability. And there have also been the addition of new established DOE sampling design methods that are newly available in this DOE capability. So what this will allow you to do is, as opposed to just being able to run a full factorial design, you can choose one of these other sampling methods that will then kind of choose a subset of trials to run that will be smaller, so you'll have less simulations, but you'll still be able to establish trends in the performance from the trial. And then there's also a new simulation manager feature that is included. This is a new capability where it will take a list of simulations and sort of queue them up, and then based on how many processors you have on your computer, it'll kick off multiple runs simultaneously, and then as soon as one of those simulations finishes, it'll get started with the next one. So this is a nice way to run through all your simulations as quickly as possible while maximizing your computing resources. And it also uses the standalone solver, so that makes it a little bit faster, just because it's not having to open the RecurDyn GUI. And then it also frees up the RecurDyn modeler licenses for other people to work on their models while you're running all your simulations. So we can just start off with defining what is the design of experiments, and that is it's a series of tests or simulations in which purposeful changes are made to the input variables of a process or CAE system so that the engineer may observe and identify the reasons for changes in the output response. And the reasons for making the enhancements to the new DOE capability is to make it easier for engineers to identify the important design variables in the MBD system, and also find the optimum design values for those variables, and then in the end to achieve robust performance for the MBD system. So I mentioned before, what's now available are some different methods for setting up the number of trials that are going to be run. And so what's still included is the factorial design. And so that includes the full factorial design, which will use all the combinations of the factors and levels. There's also a 2-level full factorial design where you're only choosing the high and low values for each variable. And then there's also these response surface design options. This is where you can select factors and levels for fitting a second order response surface. So this includes central composite design and the box and beacon design. And then there's also this random selection design method, which includes the Latin hypercube design method. And this is where it's choosing the maximum entropy sample space in the lattice space, while maintaining strength 1 or orthogonality. And so this is sort of a graphical representation of what I was just discussing as far as the different sampling methods. So here on the left, upper left, we've got the full factorial, where all the sample points are selected. And then this would be the 2-level full factorial, where only the corner points are selected. So you reduced your sample size by a fair amount. And then there's the Plackett-Berman, is where you're then choosing half of the corner points. And they're just the other methods each have their own sort of way of selecting the sample size. And so this is a fairly detailed workflow of the process that you would use when you're using RecurDyn DOE. But the graphical user interface will sort of guide you through those steps. So the first step would be to define your design variables, and then also define the performance indexes. The performance indexes is the measure measuring some type of simulation result, and then that's how you evaluate the performance of your system. So after you define those things, then you would confirm and update those design variables within the DOE dialog window. And then you select a DOE method to use and create a table containing the list of trials to run through. Then step 6 would be just to confirm the performance indexes in the DOE window. Step 7 would then be setting up the simulation parameters. And then at this point, you have the option to use the simulation manager here to run all your simulations. And so you would, if you use that option, you'd click on a certain button to open up the simulation manager, import all the RMD files that were exported in the previous step, and that would basically help the simulation manager know what simulations to run. And then there's some certain parameters for the simulation manager as far as number of cores that are available to use, and then you would go ahead and run the simulations within the simulation manager. And then after that, you would import those DOE results back into the DOE GUI, and then that's where you could review your results. You can look at the results in tabular format, or also create various plots to review the data. And then at that point, we're at step 9 here. If you choose, based on your results, if you want to refine your DOE and run a new design of experiment, then you could go back and refine your DOE and sort of repeat that, this last half of the steps. Okay, so the first step would be to define the design variables. And so this is available from the sub-entity menu under the design study section. And you'd click on this DV button. And this would basically allow you to define a list of design variables. Each design variable will be based on a particular parametric value in the model. So we're assuming that the user has already created these parametric values and parameterized their model beforehand. So once they've done that, then for each design variable, you can just basically choose this parametric value here. And then there are other controls to set the range and basically the different values that will be used in the DOE. Next is the definition of the performance indexes. That's also available from the sub-entity ribbon menu, or the tab, I guess. So if you just click on this PI button, it brings up the list of performance indexes, and then you can choose what type of performance index you want to create. The most common is to use the value of an expression as the output. And in that case, then you can go ahead and select which expression you want to use. And then there's certain treatments that you can use to grab the value from the expression. So you could, for example, you could choose to use the minimum value that the expression has, or the maximum value that it has throughout the whole simulation. And some of the other options, instead of expression, you can also choose a process net output. And so actually that's something that's used in the example we'll go through later. You can also use a scope output as well. So once those things have been defined, then here's where you would open up the new DOE capability that's available under the analysis tab. And so once you bring up this window, it would bring up a list of your design variables that you're using. And so you can basically just use this to confirm the values that you're using, or you could actually go in and further update them at this point. If you click on these buttons here to bring up the tool, then you can further edit the upper and lower bounds, also the number of points, and that kind of thing. And then after you set all your design variables, then the next step would be to select your DOE method. So this is where you'd select from this available list, such as full factorial design, central composite design. And then once you select that list, there's a button where then you would click called Create Table with DV, and that will basically create the list of trials that will be carried out based on the method that you chose. And then after you do that, actually you can further add or delete any trial that you want using these buttons on the right here. And then the next step would be to then click on the next tab, which would be the performance index tab. And this basically brings up the list of performance indexes that you've previously defined. This is more of a way just to check things over to make sure to confirm that they are what you want to use moving forward. And then you would click on the simulation tab. And so this would bring you to the step of actually running the trials that you've set up. And so some of the settings here are kind of your basic dynamic kinematic simulation settings. And then some of these are a little bit more specific to the DOE simulations, where you have the option, if one of the simulation fails for any reason, you can set the performance indexes to whatever value you want, like -1 is the example shown here. And then what you would then do is you click on this R button here, which would sort of update and show you the number of trials that you're going to run once you click the simulate button. So once you click the simulate button, then it would basically just sequentially run through all of the trials in the RecurDyn window that you currently have open. So the other option is to then use the simulation manager instead to run your simulations. And so what you would do is you would click on this simulation manager button. And well, actually, first you would click on this export file button. That would look in these directories and then generate the RMD files for those particular simulations. And then you would click on the simulation manager button, which would then open up this window here. And then within this window, you can specify a path to the RecurDyn standalone solver, and also sort of the base folder containing the models that you're running. So once that is all set up the way you like it, then you click on the start simulation buttons, and again, it would, as shown here, it's running a couple of simulations at the same time. And also there's a setting here for the number of concurrent runs. So this will be based on your licensing, and also the number of cores that are available on your computer. You would want to set this value based on that. And also, as the simulations are running, you can right-click on the different trials that are running, and there are different options that you could do for each of those. So once the simulations are complete, then what's displayed is the result sheet. If you click on the result sheet tab. And so this is basically where the user can review all the results. They're displayed in the table format here, where it lists all the design variables and the combinations of values that it's using. And it also lists the performance index results. There are also some buttons here where you can choose one of these trials, and you can enter the number here. And then if you click on update current model or create new model, that will basically update or create a new model with all the design variables set to whatever trial you chose. So if you found a good combination of design variables that gives the best results, you can quickly create a model, an optimized model. And then below here, at the lower section are various plots of the design variables and performance indexes. So these are the different plots that are available. So there's the design variable versus performance index plots. And so the user can analyze the effects of the design variables on the performance indexes. So this is the type of plot here that the user would see. And then there's the performance index plot, which plots the value of the performance index for each trial that's run. And then there's the PI plots here, where you can plot the relationship between different performance indexes. And so this helps to use, this helps the user to detect certain relationships between the performance indexes, such as any proportional relationship or inversely proportional, or you could just have some type of scatter relationship where you need to sort of select the best design from a certain area of the plot. So I'll go over an example of using the DOE, and the example is a satellite solar array deployment system, and it's going to use we're going to use the Box-Benken design method with 6 factors and 3 levels. So this is an animation showing a satellite with solar arrays that are deployed as is shown in this animation. And so the design goal here is to design an economic, efficient, fast, and safe solar array deployment system. The solar array system is controlled only with springs and dampers at these joints here to control the speed of the deployment. So that satisfies the economic requirement. All the arrays are deployed at once, so it's just a one-step deployment to make it efficient. And then we also want the deployment to happen quickly, but we also want it to be a safe deployment where the acceleration of any of the solar panels has to be less than or equal to 0.4 Gs. The satellite model is shown here, where in the stowed position you can see that the panels are connected with joints, revolute joints, and then also springs and dampers at each joint. And then the design variables are the stiffnesses of the rotational springs as well as the damping. So we have a rotational spring here, and at the base of the arm, and then a couple more springs located as we go down to the end of the last panel. And then there's also some damping value applied to those rotational springs. And then the performance indexes that we're measuring in the simulations is the acceleration of these points in the system, and then also the time to deployment. So this is a measure of, or a plot of the angles between each of the solar panels. And then what RecurDyn is going to do is it's going to look for the last point, the last non-zero point So after that point, when all the angles are 0, then the solar arrays are considered to be fully deployed at that point. And there's this is where ProcessNet is used to determine that point in time. So we're not going to actually go into detail about that, but that's just some background on that. All right, so in this example, in this, once we bring up the DOE window, we have these particular values here for the design variables. And because the user doesn't really know beforehand, what values would be good values for these spring stiffnesses and the damping, we're just assigning a large range for each of the design variables. So there's a lower range, a lower value of 100 for the stiffness, upper range of 900 used for all 5 stiffness values, and then similarly a large range for the damping. And then the DOE method selected here is the box Venken design. And then in the next tab, this is basically, confirmation that the performance indexes are what the user wants them to be. In this case, we have the first performance index is the settling time difference between each panel. I think that's something that's intended to be minimized. There's also the settling time of the entire solar array and the acceleration between each panel. So all of these things in this case are performance indexes that we want to have low values for. And then this next dialog just shows the simulation dialog used to kick off the runs. So once the user runs the simulations, they would look at these results here. And so what we're using here is the design variable versus performance index plots. And you can basically select all the design variables and just see what are the effects of changing those design variables on each of the different performance indexes. And so, for example, we can see here that for design variable 2, if you have a low level, that this creates a high value for both performance index 1 and 2. So then, based on that information, then the user can go back and modify the ranges and the values of the design variables to get a better performance from the system. So the adjustments that were made here were to basically kind of tighten up the range, but also, one of the examples we were looking at is that the second design variable needed to be higher, because when it had a low value, some of those performance indexes were very high, which was not good. So as we can see here, the lower bound for the second design variable is increased from 100 to now 500. And there are probably a couple other similar changes to the lower bounds here. So after the second DOE simulation is run, the user can use the PI performance index versus performance index plot to plot sort of the results and the relationships between some of the performance indexes. Here we're looking at PI1 versus PI3. In both of those things, we want to have low values. So in the plot, it's sort of a scatter plot showing just all the results from the trials. And we want to choose a value that's low for both the X and Y scale. And so the user can choose a point on the plot. And then when they do that, RecurDyn will highlight the particular trial in the result list. And then what the user can do once they find that good combination of design variables, they can then see that it's trial number 34. So then they can enter in trial number 34 in this text entry box here, and then basically update the current model with those optimal design variables. So once they've done that, we can see the results of the design improvement using the design of experiment. On the left here is the initial design, and then on the right is showing the improved design with the modified stiffness and damping values. So we can see the deployment is much faster after making those changes. And yeah, so that is the main improvement there. All right, so in conclusion, the new RecurDyn DOE capability will help users more easily identify the important design variables and find the optimum design values for their MBD systems. There are also various file export options throughout the process where the user can export the simulation results in a form that can be used for other data analysis processing outside of RecurDyn. And as a result of all this, users will be able to achieve robust performance for their MBD systems.